Hi, Professor. Can you hear me?
Yes, I can. Yes.
Great, great. Okay, let me open up. I think you can now see me too.
Yes, I can. Yes. I'm just trying to see how I can see myself.
Okay, great.
Show my webcam image. Audio visual. Ah, good.
Great, great. Now we can see you.
And you can hear me. So this is
Yes,
all
yes.
going very well. Excellent.
Great.
Good.
Okay. I think we can start in a few minutes.
Shall I see if I can share?
Sure, sure. On the top right, there are a few buttons. I think the fourth one is desktop sharing. If you click on it, you can share a window or your entire screen.
I've
Yeah,
got it. Brilliant. And then
yes,
that.
now we have your screen.
Ah, good. Right. But I'll stop sharing for the moment, and then, or would you like me to keep this on?
I think either way is fine, whatever you are comfortable.
Um, well, um,
Okay,
Well, I can't see you, so I'll
okay,
stop sharing for the moment, and
okay, sure.
then go back. Although now I've disappeared. Never mind. All right. I can
Okay,
still see you in the corner, so that's good.
great.
So, how many people are on your course?
About 60 people are on the course and about the same signed up for the session.
Oh,
And they
right.
are coming uh, one by one. I don't know how many would come, but we also stream on the YouTube. People on the YouTube can also watch the lecture online.
So, do you have an in-person course? Are people actually physically, on the course in the
Yes,
university? Right.
yes, yes. The course is in person. We have two lectures every week in person, but the guest lectures, because of the organizing the guest lecturer to come and do the lectures is very hard for us. We do it online.
Yes.
Yeah. We would love to do it in person, but it's hard when we sometimes when we ask persons to come on, it's not fitting their schedule and the cost and
Yeah.
the travel thing.
No, absolutely. When you get to my age, it's much easier to do it from your living room.
Okay.
It's
You're,
go
you're,
to an
you're,
airport and
okay.
it's
You're
nice
young.
when you.
You're young, professor. You're still young.
I think when you're young, it's nice to travel, but as you get older, then you sort of tend to prefer to stay at home and just
Okay.
remember all the exciting places you visited.
Great. We would love to host you in Sheriff if that's the possibility. If
I think I'm too old now. I'd have to send all my younger people who can go and party with you and explore restaurants and things.
okay, yeah, well, we would love to run a party for you if you come and show you. I don't know if you have ever traveled in Iran, traveled to Iran.
Um, no, I've been to Tehran, but not Iraq. No, no, I haven't. No, that's one of the few countries I haven't been to. That's but I can use Google Maps now to explore if I need to. So,
experience is different. If
I can imagine.
we, we have lovely places that we can take you on if you ever decided to come and visit.
Thank you.
Sure. Mm, I'm just starting the checking the YouTube stream and then I think we can start. I think everything is fine. If we can start. Okay, so welcome everyone, and we have the honor of hosting Professor Friston for today talk, and we are very honored to have you here with us, Professor. And I think without further ado, we can have your wonderful talk.
Thank you very much. Well, thank you very much for inviting me. Let me just share my screen and then we can get going. Excellent. Well, let me repeat my thanks for being invited to talk to you. It's a great pleasure and honor. I am aware that this is a deep reinforcement learning course, so you will have to forgive me. I'm not going to talk exclusively about reinforcement learning, but more about the physics of self-organization that put reinforcement learning in context. So this is going to be a theoretical talk. I am told you need to hear it about 3 or 4 times before the simplicity of the message becomes apparent. And perhaps I'm going to motivate the story I want to tell by a reference to Geoffrey Hinton's response to a question. So Geoffrey Hinton was presented with the UCD Ulysses Medal a few months ago, if not a year or so ago, and he was asked at the end of his lecture if he could go back in time and meet somebody, a theoretician, who would he like to meet? And this is his response. Now, you won't be able to hear it at your end, so I'll read what Jeff is saying. I'd like to meet Helmholtz. He believed in unconscious perceptual inference. He thought that vision involves many inferences. One infers from the proximal stimulus the state of the world that generated it. Another aspect of Helmholtz's work concerned free energy. But what he didn't know was that to infer a complex model, a statistician would advise you to do the inference by determining the best way for your model to explain the data. And a model can have multiple ways of explaining the data. You need to determine the probability of each of these ways, and variational inference approximates the probabilities while ensuring model improvement. So the two completely different aspects of Helmholtz's work, namely free energy and perceptual inference, are closely related. And free energy is the key to perceptual inference, and I would have liked to have told Helmholtz this. And then the audience applauds at the end for that insight that at the end of the 19th century, there were the germs of a description of self-organization and inference, sense-making and decision-making. And that's basically the story that I want to tell you today. And the story I'm going to tell, I'm going to tell the story twice. First of all, I'm going to explain the importance of free energy in terms of sense making and self organization in a way that a physicist would understand by focusing on the statistics of life with a special emphasis on Markov blankets and the Bayesian mechanics that attend Markov blankets. And what we're going to see is that in order to find anything or any self, in terms of self-organization, we need to disambiguate the thing or the self from everything else or the non-self. And that's where the Markov blanket comes into play. I'm then going to repeat the narrative from the point of view of computational neurobiology and psychology and possibly machine learning, with a particular emphasis on predictive processing, or specifically predictive coding formulations of sense making and evidence accumulation in neuronal networks. And then finally, if we have time, I'd like to turn to action and perception in the spirit of active sensing or active inference, and the bright line between artifacts, things that just make sense of their sensory input, and those things that actually act in a way to sample the particular input that they are making sense of. So, where should we start? Well, let's start with this question posed by Schrödinger. How can the events in space and time which take place within the spatial boundary of a living organism be accounted for by physics and chemistry? Now, I'm not going to answer that question, but I am going to pick out the notion of a spatial boundary, noting that in order to talk about anything, you need to be able to disambiguate or individuate that thing from everything else. And that implies a boundary that I'm going to read as a Markov boundary or a Markov blanket. So what is a Markov blanket? Well, effectively, it's a statistical boundary, possibly best illustrated with this little schematic here, where the circles represent states of some universe. And these states are weakly coupled in the sense that this state can influence the dynamics or the changes in this state. Now, if I am now given a set of states in this little world, if I now identify some set of internal states, say my internal states, then the Markov blanket comprises the parents, the children, and the parents of the children. And put simply, what this Markov blanket affords is a statistical separation or insulation of the internal states from the external states. Technically, what we're saying is that given the blanket states, the internal states are conditionally independent of the external states. Another way of putting that is, if I wanted to know how I'm going to evolve, I only need to know my blanket states. I don't need to know the rest of the universe. I'm going to make a further move here. I'm going to divide the blanket states into sensory states that influence but are not influenced by the internal states, and the active states that influence but are not influenced by the external states. And together, we now have a particular partition, a partition that you could apply to anything or any particle, for example. And this partition comprises the external states and the states of a particle that can be divided into internal states and blanket states, where the blanket states themselves can be partitioned into sensory and active states. So why have I done that? Well, if we think about our favorite, my favorite system or particle, the human brain, we can associate all the internal states of my brain, for example, all the synaptic activity, all the connection weights or connection strengths, um, with the interior or the inside or the internal states. And according to this Markov blanket partition, the internal states will influence the active states, for example, my actuators, my autonomic reflexes that allow me to move and change the external states that themselves then reciprocate and change the sensory states, the states of my sensory epithelia or my sensory input or um, my the content that I sample. So what we have here is a nice partition between things on the inside and things on the outside that are conditionally independent and separate, yet at the same time influence each other vicariously through these sensory and active states. So the inside influences the outside through action, and the outside influences the inside through sensation or the sensory states. What I'd like you to do now, though, is for a time, forget about the Markov blanket partition. What we're going to do is just do a very brief review of physics of random dynamical systems, and then we're going to put the Markov blanket back into play and see what kind of mechanics emerge from that. And what we're going to see is a Bayesian mechanics. But let's just start from the beginning. Let's just imagine there is some universe with lots of states in a vector x that changes in a lawful way as a function of x, plus some random fluctuations. And I've cartooned this here in terms of just two states that could represent many states, say my states, at many different scales. So for example, this could be very fast oscillations of a nerve cell in my brain. It could be two states of my heart, and it could be a cardiac cycle, or it could be me getting up in the morning and doing my emails, having lunch, and so on. This kind of description, as we move through state space, affords a picture, a mathematical image of the kind of systems that we want to characterize. And in all of those examples, the key thing is that my states keep revisiting states that they were once in. In other words, there is a set of states to which I am attracted in some kind of itinerant way. Technically, this is known as a pullback attractor and characterizes these non-equilibrium steady states. I've just described this in terms of my states tracing out a trajectory in state space, but I could also interpret this as a probability density in the sense that if you sampled me at random, then the probability you will find me in this state corresponds to the density of these trajectories, or the density, the probability of finding me in this state, given that I am me. And that's important because we know a lot about the physics and the maths of how this probability density itself evolves over time. Um, and I'm illustrating that here in terms of the rate of change of the probability density expressed in terms of the Fokker-Planck equation, where the rate of change of the density is a function of the flow of the states and the amplitude of the random fluctuations gamma here. So why is this important? Well, if I've just said that we are interested in describing self-organizing systems that possess a pullback attractor, then this probability density does not change with time. It is always the same, which means I can set this to 0 and solve this equation. So what does that give me? Well, it gives me something really interesting. It gives me an expression for the flow of my states, my dynamics, in terms of the amplitude of the random fluctuations and the gradients of the logarithm of this probability density. You'll notice here that there are two terms that pre-multiply these gradients. This is the amplitude of the random fluctuations. There's another term here, and this term is due to the Helmholtz decomposition. This term corresponds to conservative, non-dissipative, or solenoidal dynamics. And just to make this clear, let's just turn to an everyday example of this fundamental decomposition of gradient flows into conservative and dissipative parts. So if you imagine water flowing out of your bath, there are two kinds of flow. One is down potential energy gradients, and this would be the dissipative flow, the gradient flow controlled by the degree of random fluctuations. And the circular flow would be the solenoidal flow. And this effectively is the flow around the isocontours of this probability density. So all we're doing is we're just saying that the flow of states is at steady state divided into two things that are orthogonal at right angles. One, climbing up probability gradients to resist the dispersion of my states due to the random fluctuations, and then circulating around the isoprobability contours. And that's basically the basis of everything that I'm going to say. So what about the Markov blanket? Well, that basic decomposition holds for all the states, including the components of the states of that Markov blanket partition. And in particular, because of the way in which that Markov blanket is constructed, the internal and active states do not depend upon, nor are they influenced by the external states. So I can now write down the dynamics of my internal states and my active states as effectively this augmented gradient flow on the log probability of my blanket states or my sensory states here, given I am me. And the argument here is that we can read this as basically a description of action and perception, coming back to this circular causality, the inside influencing the outside and the outside influencing the inside. And that's, I think, a simple but quite pleasing description of self-organization viewed through the lens of perception and action, or sense-making and decision-making, for example. Why is it nice? Because it's very inclusive. If I just think about what it means to perform a gradient flow up these log probability gradients, it means that I will look as if my perception and action are both trying to increase the probability of the states that I occupy, given I am me. So these are the states that characterize me. They're attractive to me. They have value to me simply because these are the kinds of states that characterize the kind of thing that I am. So I could read these as being valuable states, or the log probability being value. And all this equation is saying, or these equations are saying, is that you can interpret this in terms of things like reinforcement learning, where we're maximizing expected value. If I was an engineer, this would be optimal control theory. If I was an economist, it would be expected utility theory. What about the negative of this log probability? Well, if you did information theory, you'd recognize this as something called self-information, sometimes called surprisal, or more simply surprise. It just scores the implausibility of this sensory event or outcome given I am me. And indeed, this is where the free energy comes in as a bound approximation, or in the limit, a score that corresponds to the surprise. So this interpretation of this quantity that is being effectively maximized fits very comfortably with information theoretic accounts of self-organization, such as the INFOMAX, or maximum mutual information principle, equivalent to minimum redundancy principles, and in virtue of this bound here, the free energy principle. In turn, the average surprise over time is called entropy. The average of the self-information, the expected self-information, is called entropy. So all this is saying is it will look as if I am self-organizing to minimize the entropy of my sensory states or my blanket states. And this, of course, is the holy grail of self-organization of the kind you would find in synergetics in terms of things like laser physics. And if I was a physiologist, it's just a statement of homeostasis. It's just the statement that self-organization entails the resistance to the dissipation or the dispersion of my essential variables. Excuse me. There's a fourth interpretation that I want to pursue here, and that's the interpretation of this quantity, the probability of some sensory input given me, which a statistician would interpret as the evidence inherent in these sensory data given me as a model of the causes of that data. So in Bayesian statistics, this will be known as model evidence. And this means that we can now interpret perception and action as maximizing the evidence for me as a model of my world. And from this, we can spin off the Bayesian brain hypothesis. We can talk about these dynamics being an instance of evidence accumulation and all the particular formulations, for example, predictive coding, which we'll focus on in the remainder of this treatment. So that's the basic physics story. I'm now going to tell exactly the same story, but using concepts and intuitions that are more commonly found in psychology and computational neurobiology, with, I repeat, a special emphasis on predictive coding implementations or descriptions of this basic gradient flow that inherits from the Helmholtz decomposition. So the anatomy of inference. Let me start here. I could start with Plato, but I'm going to actually start in the 16th century with this oil painter, famed for painting still lives, that when viewed from a different perspective, give you a very different visual impression. So if previously you saw a bowl of fruit, but now you see a face, the point being made here is that you made that face. You on the inside generated a hypothesis, a fantasy, an explanation for this particular pattern of sensory impressions on your eyes. So the notion is that perceiving, sense making, is very much an inside out process. It's not an outside in process where you're extracting information. You are constructively creating explanations for the sensory impressions and then testing those predictions against what you're actually sensing to effectively find the best explanation for your sensory data. And this notion, which probably can be found in philosophy in Kantian notions, to my mind was most beautifully expressed by Helmholtz. So this is where Geoffrey Hinton was referring to unconscious inference. So for example, objects are always imagined as being present in the field of vision, as would have to be there in order to produce the same impression on the nervous mechanism. So again, what he's saying is it has to be there on the inside in order to predict or reproduce what you would see if your hypothesis was correct. And clearly, this is very closely related to the notion of perception as hypothesis testing due to people like Richard Gregory, ideas that have been taken and used with great effect by people like Jeff himself and Peter Diane, who actually built a Helmholtz machine as a metaphor for the Bayesian brain, borrowing from Bayesian probability theory, and in particular with a nod to the work of Richard Feynman on variational free energy as a way of rendering Bayesian inference a tractable optimization problem. But let's, for the moment, just come back to this notion of producing impressions on the nervous mechanism. So from our point of view, from the point of view of the Markov blanket, what we're saying here is that one interpretation of this statistical reading, this Bayesian mechanics reading of maximizing Bayesian model evidence, sometimes referred to as self-evidencing, can be understood as a description, or can be thought of, interpreted as trying to explain what caused these sensory impressions, these shadows on my Markov blanket, on the sensory sector of my Markov blanket. So is this a leaf or is this a bird? And I have to now infer the most likely cause that's beyond my skull-bound brain. So how do we do this? Well, we know how to do it because we are something, we are a self-organizing system that possesses a Markov blanket. We have that aspect of thingness, and therefore we know that our internal states have to comply with this Helmholtz decomposition. What I've done here is just replace the log probability with the free energy here, and we'll see how that is licensed mathematically in a few slides. And I've made a further move. I've just said that I'm now going to interpret my internal states as parameterizing a probability distribution, some Bayesian belief about the external states, about the causes of my sensations. And this Helmholtz decomposition now assumes or can be re-expressed or rearranged in a form which, if you were an engineer, you'd recognize as a Kalman filter or a Bayesian filter. So what do I mean by that? Well, the solenoidal part can basically be understood as if I had some expectation, some internal representation of the outside world, then I can predict how that is going to change in the next moment in terms of its rate of change here. And that will be a prediction. But I can also update that prediction based upon what I actually sample. And that update is the dissipative part, the non-conservative part, that is this gradient flow, the flowing down free energy gradients, where the gradient is just a prediction error. So what's a prediction error? Well, imagine we had this sensory impression on our retina, and I had some internal brain state that encoded the hypothesis or the Bayesian belief that it was caused by a howling dog. And if I had a generative model that could generate the predictions of what I would sense if my hypothesis was right, then I can subtract the predictions from the actual sensations, and the difference is just the prediction error. And all this equation is saying is that the prediction error can be interpreted as driving changes in my internal states, effectively to do Bayesian belief updating, so I've got a better explanation. So effectively, we're destroying the gradients, finding these free energy minima, at which point I can't reduce the prediction error anymore. And if that's the case, I've now got a good enough explanation for what could have caused my sensations. Notice that I'll never actually know what caused my sensations. In this example, it was not a dog, it was a cat. And that doesn't matter. If I can get through life explaining everything in terms of what I think caused my sensations, that's good enough from my point of view. So this notion of destroying free energy gradients or performing gradient flows on variational free energy, namely in this formulation prediction error, is very nice because it means we can forget about all the physics and just summarize action perception as in the service of minimizing prediction error. And there are two ways I can minimize prediction error. I can either change my mind to make my predictions more like the sensations, and we can associate that with perception, or I can act on the world to sample some new sensations that are more like my predictions. Both will minimize the prediction error. And this provides a very simple but compelling view of action, where I'm just acting in a way to change my sensations such that they conform to my predictions. So I have an inherent bias towards making my predictions come true by active sensing or active inference. And this is the inactive aspect of this kind of Bayesian mechanics or self-evidencing that comes from the free energy principle. Um, Here's a particular example for the neurobiologists in the audience. It's a little brain, just to show how this actually unpacks or unfolds in predictive coding networks or neural networks or neuronal networks in this instance. Let's just start from one kind of sensory input. So that coming from the retina, visual input that comes into the lateral geniculate nucleus, and it's in receipt of some top-down predictions here so that I can form a prediction error. And then this prediction error, according to this Helmholtz decomposition and gradient flow here, is then going to be used, or it's going to change my expectations so that the prediction error is self-destroying, self-eliminating, or is resolved. However, these expectations themselves are now in a hierarchical or deep generative model, themselves being predicted by higher order expectations, so that I have second order prediction errors that now themselves are used to inform and update the expectations, and so on to any hierarchical depth. So what this equation suggests when we unpack the generative model entailed by this predictive coding interpretation is that we can understand message passing on neural networks in terms of top-down predictions that are generating prediction errors that then ascend in a bottom-up way to improve or optimize the expectations that underwrite the descending predictions. So this would be an apt description of sense making or perception. But what about action? Well, let's just consider another kind of input, proprioceptive input, that comes from the stretch receptors in my eyes. So this could come in, it could come into the pontine nuclei, it could be in receipt of top-down predictions, and I now have a proprioceptive prediction error. And I could use that proprioceptive prediction error to update my beliefs about where the pose of my eye or where I was looking. But there's another much simpler way of resolving proprioceptive prediction errors. I can simply send them back out to activate the muscles that are responsible for setting the stretch until the muscles contract in a particular way that my predictions of the state of my muscles are actually fulfilled reflexively. So what I'm describing here is a classical reflex arc, where the predictions now are realized, they supply the set points for peripheral reflexes that fulfill the predictions, so that I'm now changing the world as opposed to changing my mind. And this is basically the active part of this active sensing or active inference. So let me now give you an example of this kind of active inference and ask whether it is sufficient to explain or describe at least the kind of decision making that things like you and me engage in. So here's a numerical example, a very simple example of this kind of reflexive active inference. And what we've done here is just to build a little synthetic agent, and this agent had a generative model based upon effectively a central pattern generator that exhibits a series of unstable fixed points that were then mapped to extrapersonal space. And then furthermore, this point in extrapersonal space under the generative model of this agent pulled with an invisible spring the agent's finger. So what we've built, what we've specified here, is a generative model that will generate predictions in two modalities, in terms of the visual modality that the finger will be drawn around in a particular pattern, but also predictions in the action domain or the proprioceptive domain, where the agent predicts that it will feel its finger being pulled around. And if I equip this agent with reflexes that realize those predictions, then the agent will actually move to fulfill the predictions, but also in moving will also supply the visual input, the sensory impressions that the agent predicted. And effectively what we have now is a generative model that's actually authoring its own sensations. So on this view, the descending predictions in the proprioceptive domain are fulfilled through action, and the predictions in the visual domain are confirmed as a consequence of action. Sometimes this is also called corollary discharge. This is a nice example, and here contrived um, to simulate an agent writing the letters J and A. It's a nice example because it allows us to perform synthetic lesion studies. And here's this one example. What we've done here is first of all plot the activity of these neuronal populations or nodes in a neural network, um, and choosing one and showing whenever its activity surpassed half maximum, and showing that it selectively responds to particular directions and places in the field in which it is moving, in the visual field of action person space. And this is a ubiquitous finding in the neurosciences, framed in terms of receptive fields, or in this example, place cell activity. The interesting thing is that if I now remove the proprioceptive prediction errors so that the agent is seeing the same thing but can no longer feel itself move, it will be as if the agent is watching somebody else move, which would be like in the neurosciences, observing another person act. But the generative model is perfectly fit or apt for predicting the visual consequences of another's action. And we can show that by just simulating action observation and showing that exactly the same selective responses are elicited during action observation. This may not be relevant for reinforcement learning, but it is an appealing example of something called the mirror neuron system that enables underwrites things like imitation learning or inference of intentionalities. When you see somebody else do something that makes sense if you know why you would be doing exactly the same kind of action. So is that kind of demonstration and that reflexive sort of active inference a sufficient account for decision making and planning and acting upon the world? And I would submit it's not. There's a distinct difference between just responding reflexively and actually thinking about the consequences of your action, and then selecting that action which you think you are most likely to commit to. So how can we get to this more sophisticated kind of decision making and choice and explanation for choice behavior of the kind that you would be addressing in reinforcement learning? The way that I'm going to get there is just to make one very simple move. I'm going to assume that the system that we're talking about is sufficiently large that the internal states can no longer see the active states. So they become hierarchically separated when we have a deep generative model on the inside that is constituted by the internal states. So I'm just going to remove this arrow here. And that has a really interesting consequence, because now if we take this free energy perspective or active inference perspective, that the internal states are always representing the causes of the sensory states, now my own action becomes a vicarious cause of my own sensations. And that means that I can now represent my own action. And that's important because I've now separated action as a real variable from my internal representations of action as a random variable about which I have beliefs that I have to infer. And if I'm inferring my own actions, effectively, I am planning. And I can roll out into the future and plan to do this or do that, provided I have a generative model of the consequences of my action. And this draws a bright line between different kinds of Markov blankets or different kinds of things. And one could argue it's a bright line between sessile things or things, for example, like microbes or single cell organisms, where the active states, the internal states have direct access to the active states, and other kinds of larger phenotypes or animals or true or authentic agents where we don't have that access, and we have this kind of organization where now my posterior beliefs encoded or parameterized by my internal states now include my own action. So what are the priors over my own action? Well, if I am a free energy minimizing, self-evidencing kind of object because I simply exist and I have these characteristic or attracting sets, my pullback attractor, then I am more likely to engage in those actions that will minimize the free energy I expect after taking that action. And it has to be an expectation because the consequences of action are no longer observable. They're no longer sensations. They now become random variables in the future. So what would the expected free energy look like? So what I'm doing now, and if you don't like equations, please forgive me, you don't need to understand the equations. I just wanted to show this slide just to unpack the variational free energy as an objective function that underwrites perception, and expected free energy that underwrites action, and to show the symmetry or the different ways that you can interpret these two free energy functionals. So let's just start with the free energy. Um, why is it a bound or an approximation to this value or negative value or log evidence here? Well, I can write down the free energy basically as a KL divergence, a difference between two probability densities, conditional probability densities in this instance, um, plus the thing that is being bounded. So this expression here would be something that people in machine learning would recognize as an evidence bound. The negative free energy represents an evidence lower bound. Because this quantity, this divergence can never be less than zero. So that's sometimes known as an elbow in machine learning. It's the kind of objective function used in variational autoencoders. But I can rearrange this bound on the log evidence to express it in a way that a statistician would understand. And she would say, this free energy functional is just a mixture of complexity and accuracy, where complexity scores the degree to which I've had to change my mind in moving from a prior belief about the causes of my content or my data or my sensory impressions, and my posterior beliefs after seeing something that could depend upon action. So this just scores the degrees of freedom I'm using up in creating an accurate explanation for the causes of my sensory input. In other words, we can also decompose the bound on the log evidence into accuracy minus complexity. The reason I'm going into that is that when we now take the expected values, expected under the predicted posterior of outcomes in the future or observations in the future, the complexity becomes risk, the inaccuracy becomes ambiguity, and the divergence and log evidence become intrinsic and extrinsic value, respectively. So what do these terms mean? I suspect that you have seen these terms many times before in different fields, but let's just go through and start off by ignoring the extrinsic value, by ignoring the attractiveness or the value or the the value for me of a priori getting these sensations or being in this state. And what are we left with? Well, we're left with this another KL divergence. What between? Well, between my Bayesian beliefs about the causes of my sensations with the sensory information that would ensue if I took this action relative to not having that sensory information. So this KL divergence scores the information gain that I would get if I committed to this particular action. In the visual search literature in neurobiology, this is also known as Bayesian surprise. It's also just the mutual information between the sensory consequences of some external causes that would ensue under a particular action, coming back to the information theoretic interpretation of this self-evidencing process. Let me now take a particular kind of uncertainty off the table, and I'm going to remove ambiguity. How can I do that? Well, I can assume that in some special worlds, I can see all the external causes. So there's no ambiguity given my sensory input about what caused. There's no sensory noise. I see all the external states. So I can now remove this, and I'm now left with this. So in this particular case where I've now removed ambiguity, I'm now going to choose those actions that minimize this KL divergence. What is this KL divergence? Well, it's just the difference between what I expect to happen if I took this action relative to a priori my preferred states or outcomes or the causes of those outcomes. So in engineering, this is known as KL control, and can be related in economics to risk-sensitive choice or risk-sensitive control. And it just scores the divergence from prior preferences. I'm going to make one more move now and take the last kind of uncertainty away, and that's the uncertainty that is scored by this intrinsic value, this Bayesian surprise, this expected information gain, this resolution of uncertainty, sometimes referred to as intrinsic motivation or epistemic affordance, the things that underwrite the information seeking and the exploration that we see that is part and parcel of active inference or self-evidencing. If I assume now that there is nothing more, there's no more information in this world, I've become very, very familiar in this eco-niche, in this setting, then I'm just left with the extrinsic value, which of course is just the expected value here framed in terms of an economic perspective, or it could just be the expected reward consequent upon this particular action here. And we could read that in terms of either reinforcement learning or expected utility theory. But notice what we've done here. In order to reduce things to expected utility theory or reinforcement learning of the kind that you might see in the Bellman optimality principle, we've had to suppress all different kinds of uncertainty, either the ambiguity or the potential information gain that is afforded by particular actions. So let me close with an example of this. And the example comes from the visual search interpretation, where we can now read this intrinsic value as intrinsic motivation that scores the expected information gain as opposed to the expected value. And that means that I can actually evaluate the intrinsic motivation or value of different actions. So in visual search, each action could be looking at a different part of this image. And imagine I could only see a small part. So if I looked here, I could see this part of a subimage. And if I now wanted to score the salience, the epistemic value of looking over here, I could score that in terms of how much uncertainty would I resolve if I got the information from here in terms of my hypothesis about the cause of this particular sensory sample. And I can just move this around and measure the information gain. And I can treat that now as basically the negative expected free energy and create a map of salience. And this, in fact, does account for the way that people, things like you and me, actually explore our environment through visual palpation with saccadic eye movements here from the classic work of Yarbus. And we can simulate that. And I've simulated that here with an agent that has a very simple world. In her world, she can be looking at a face, but the face can either can only be upright, upside down, or on its side. The problem is, or the restriction, the constraint, is that she can only see a very small patch of the image at any one time. So has to choose very carefully using this expected free energy, and in particular the expected information gain, where to look next, what's going to provide the best kind of information for resolving hypotheses among the three different possible explanations for these sequentially sampled, in this instance, images. And this is where she chooses to look, or the synthetic agent chooses to look, and this is what is actually sampled here in terms of the foveal representation, shown as a sequence of time at the top, and the changing salience maps that obviously change as I get more and more confident, or the agent gets more and more confident um, um, about the information available. Then she's not going to revisit places that she's already gone because there's no information gain. So this salience map changes, and changes in a way that underwrites an optimal resolution of uncertainty both within and between these saccadic eye movements until the Bayesian credible intervals shrink sufficiently to make this agent confident she's looking at an upright face, which indeed she was. So that's a biomimetic example of this kind of exploration um, that is driven purely by the expected information gain that is part of this expected free energy conditioned upon action. So I will close by summarizing everything that I've just said much more succinctly by using a quotation from Helmholtz. Each movement we make by which we alter the appearance of objects should be thought of as an experiment designed to test whether we have understood correctly the invariant relations of the phenomena before us, that is, their existence in definite spatial relations. And with that, it only remains for me to thank those people whose ideas I've been talking about, and of course to thank you for your attention. Thank you very much indeed.
Thank you, dear professor, for your wonderful talk. I think now we can open for the question. If the audience have questions, please raise your hand. Honestly, most of the content was new for me, and it's hard for me to come up with interesting question to ask. I just wondering what inspiration can we take from the ideas that you explained to us that we can apply to making intelligent systems that we engineer.
Well, I think the key inspiration is um, there are two. I think the first thing is that you can generalize the objective of building artifacts that display optimal behavior through treating everything as an inference problem under a generative model, including, when I say treating everything as an inference problem, I mean that you can combine state estimation, sense making with inferences planning so that you're not now just reinforcing particular behaviors in terms of a state action policy, but you're now incorporating uncertainty and information gain in the objective function. So from the point of view of reinforcement learning, it will be like supplementing the reward with an information gain term. So uh, the the importance of this expected free energy or free energy formulation is that you're now reformulating reward in terms of a log probability, in terms of the probability that something like me would encounter actively or seek out these kinds of outcomes. So there's always a mapping between a reward function or a cost function or a loss function, um, and some um, implicit log preference or log probability. And as soon as you do that, because the information gain is a functional of probability distributions, it has to be because it scores the information gain. Um, and now your reward is also a function of a probability distribution. That means that they have the same units. So now you can talk about the optimal balance between the expected information gain and the expected value, where the value is now defined in terms of a log preference or prior over this outcome relative to that outcome. And that means when you instantiate these this sort of generalized reward function, this that is now equipped with this intrinsic motivation as opposed to the extrinsic motivation supplied by the reward function or the cost function, what you tend to see is a systematic change from exploratory behavior to exploitative behavior that is Bayes optimal. So what happens is as the agent starts off in an unfamiliar or unknown environment, it will act in a way under constraints that it doesn't encounter very aversive, non-preferred, um, high expected cost. So it's always constrained, but it will explore under the constraints of your loss function to maximize its information accumulation about the environment. But as time goes on, there's no more information to be accumulated. So the extrinsic, the exploratory part of the expected free energy falls, and at some point it falls below the expected reward or expected value. And then suddenly there's a deterministic switch. So the agent now starts to exploit. Says, I'm bored with this exploring this environment. I'm now going to act in a way to secure my rewards. And will continue doing so until the environment changes. All that mechanics, which has a lot of explanatory power, rests upon being able to to resolve the exploration exploitation dilemma by putting rewards in a space of probabilities and log probabilities where effectively they become potentials. So that would be one intuition. The other intuition here would be that in doing that, you now have a Bayes optimal reinforcement learning. So you could look at this as a kind of sort of Bayesian RL. I mean, Bayesian RL has many, many different interpretations. I would imagine that the ultimate description is this active inference of this expected free energy functional. And the nice thing about that is that sort of carving it into an expected information gain and an expected value with the same units, which incidentally are natural units because we're working with natural logarithms. So they're like bits of information, as it were. So you can score this reward in terms of either natural units, or bits of information. And similarly, you can understand then the information gain in terms of how many rewards does that mean. But the nice thing about decomposing the expected free energy into expected information gain and expected value is that you're now Bayes optimal in the dual sense of, first of all, Bayesian decision theory, and that would be the expected value part of it. But there's another kind of Bayes optimality called Bayesian optimum design, or optimal Bayesian design principles, and it's those that design principles that underwrites active learning. I don't know if you've come across active learning, but it's choosing the next data point that will resolve as much uncertainty as possible about my about the underlying structure that I'm trying, whether it's a sort of curve fit or whether it's latent causes. Um, so active learning is basically the part of Bayes optimality that complies with the principles of optimal experimental Bayesian design, where you're designing an experiment that gets the best kind of information to resolve, to maximize the information gain. And of course, that's exactly what I was using with the eye movement. So each eye movement is just a little experiment. It's, go and get data from over there and make sure it's the best data under this principle of optimal experimental design. So it's like active learning, but in the context of fast inference. So that's another perspective. Practically, what that means is you might want to look at how would you implement this on a neural network. And what people generally tend to do is they pick a particular inversion scheme, such as predictive coding, and see if they can interpret, say, back propagation of errors, or the kind of optimality you get from machine learning, using a predictive coding formulation. However, what happens is, because the approach I've been describing is effectively predicated on a generative model. That's the second important sort of inspiration, if you like, that you always start with the generative model. If you can write down the generative model, the inversion of that and everything I've told is off the shelf. You have to specify the generative model. But of course, if you're doing machine learning, you're sort of given the generative model because you're given a deep network, for example. So now you have to reverse engineer what is the underlying generative model that you're now trying to optimize in relation to some sensory input or some content, and the ensuing responses. And when one drills down into deep neural networks, that basically applies a hierarchy. And then when you think about the predictive coding optimization and learning of that model, then you realize all the updates are local. So now you get a different kind of learning scheme, which is not back propagation of errors, where everything is working locally. So there's quite a lot of work in some groups, largely theoretical work. So trying to reproduce, and possibly in small problems outperform back propagation of errors using exactly that predictive coding formulation of optimization, focusing on the learning of the parameters of the generative model. So there are a couple of inspirations. If I don't know if they're very useful, but that's.
No, they're great. Thank you. Thank you for stating that for us. Thank you. We have two people that wants to ask question.
Uh, Hello, can you hear me? Is my voice clear?
Yes.
First of all, thanks for your excellent presentation. I found this topic really interesting, and I had searched about it before, but I couldn't find any of these things that you mentioned in this session. My first question is, can you give me some keywords and some resources to further explore this area, because I have searched in ChatGPT and Google and stuff like how mind works and some neuroscience stuff, but none of these idea like Markov blanket came into those results. So I'm really eager to learn more about this kind of topics.
All right, excellent. Yeah, so usually the reading material and the background maths comes in two flavors. You can either do it from the point of view of the physics of self-organization, and that would be come under the heading of the free energy principle. So usually without my name, but if you get lots of free energy principle hits, then put my name in it, and it'll focus on the free energy principle at hand. It's a free energy attributable to Richard Feynman, so it's not a Helmholtz or Gibbs free energy. It's the kind of free energy that Richard Feynman used to solve the path integral problem when he was doing his quantum electrodynamics. So that's now known as the free energy principle. if you want more of an applied, not quite, well, yes, machine learning like approach that is focused on sort of understanding how agents behave, and in particular, you know, uh, how one can understand things from the point of view of cognitive neuroscience. That's called active inference. And if you Google active inference, you'll hopefully come across a book called Active Inference. But probably more importantly, there's a Californian institute called the Active Inference Institute. It's just run by volunteers. It's a sort of not-for-profit institution that's just run by a few volunteers. But their mission is to provide didactic materials and lectures that are related to this, and they have a lot of educational resources and learning resources, and also teaching. If you wanted to start teaching or mentoring students in the active inference field, then they would be a great set of people to work with. And they have a worldwide. It's a small community, but it's a growing community. There's also an active inference international workshop that this year is going to be in Toronto in Canada, which is another good place to sort of see what's going on and what kinds of things people are interested in. That can range from reinforcement learning right through to emotional inference, inferring what my emotions are at the moment and how that contextualizes my choice behavior.
Okay, thank you for that. And I have two other questions. I try to ask them as quick as possible. The first one is about free energy principle that we are talking right now. You said that it's not equivalent to Gibbs energy that we have in thermodynamics, but I have in mind because thermodynamics Gibbs energy is kind of explaining all the stuff in the world, at least to limited knowledge of mine. I want to know, is it any kind of similarities between Gibbs energy, what is entropy there, and the energy itself, the thermal energy? Can we have kind of mapping between these two?
Yes, you can. In fact, by coincidence, I've just been writing a response to a behavioral and brain science paper making exactly this point. So a gentleman called Anil Seth has just written a BBS paper about, can artificial intelligence ever be conscious? And he ends up with exactly that question that you've just asked. And it's a great question. Yeah, absolutely. There is actually a lawful and monotonic relationship between the variational free energy in the sense of Feynman and in the sense that I use it in the free energy principle, and the thermodynamic work. So very briefly, the free energy, the variational free energy, is a functional of some representation, some Bayesian representation that is parameterized by the internal states. And as I described, it supplies a bound upon the log probability of things, the Markov blanket, for example. That log probability is always a potential. It's a potential energy. So the free energy that we're talking about plays the role of a bound on a potential energy. And that means a change in the free energy always entails a change in the potential energy, and that always entails thermodynamic work. And that can, if you like, be related to the thermodynamics, the thermodynamic free energy. You can then get into all sorts of interesting arguments, or not arguments, but conclusions using things like the Jarzynski equality, which says that to change the probability distribution of a system, you have to do work. And that applies exactly to the change in free energy that entails a change in the potential. So there's a very, very close relationship. However, I don't want to overstate it. Remember, the variational free energy is a free energy functional of a probability distribution that is parameterized by internal states. It's not the free energy, the thermodynamic free energy of the probability of internal states. That also behaves in the same way as a variational free energy, but it's a very different kind of thing. It's the kind of thing that I use in brain imaging. So if I do a brain take an image of your brain while you're doing a particular decision-making task, I can see various parts of your brain light up because they are doing work. They are um, changing the thermodynamic free energy. So that would be the sort of the Gibbs free energy part of it. That goes hand in hand with the Bayesian belief updating that changes the variational free energy, but mathematically they're very distinct quantities. They just share the same minima. And so it's a subtle question, and I'm not sure that everybody has the exact answers, and but there is certainly a deep connection between the thermodynamics of belief updating and the uh, variational treatment of belief updating in terms of things like the pathogen formulation.
Okay, thank you for that. And it comes to my third question that you mentioned in your answer, which is what is the role of free will and consciousness and stuff like that in all these modelings? For example, the Markov blanket that you said, or the other ways in the free energy that we are talking right now. Is there any room for free will, for consciousness, for things like that that we try to have kind of metaphysical point of view on them, or can we interpret them using the mathematical tools that we have right now?
Yeah, again, excellent question. I don't really do consciousness research, and I don't have a philosophical training. However, there are people who have applied the free energy principle to questions in consciousness, and there are a number of interesting applications which, if you're interested in this, I think you would find engaging. For me, some of the important ones are, first of all, free will. What does it mean to have free will? It means the ability to select. Where would you select in the context of active inference? Well, you'd select the policies. Do you remember that I was saying that one can score this policy or this action with the expected free energy, and then you can do it with another action and another action before you commit to it. So these are all counterfactual actions that you haven't yet done, but you can score by rolling out into the future to evaluate the expected free energy. It's very much like expected reward in reinforcement learning. You're rolling out into the future under some assumptions about what will happen if you do that. So in active inference, you do that for a number of plausible policies, and then you can interpret the selection of the policy with the smallest expected free energy, or the greatest sum of the expected information gain and expected value. You can interpret that as Bayesian model selection. So I think you've got a mathematical image of selection in this planning as inference under this expected free energy formulation that can, and I think that would define true agency. That's what I meant by authentic agency. When there's a separation, when you start representing your own actions as random variables, and you have a generative model of the consequences of your actions in the future, then you can now select among different policies. And I think at that stage, you could easily argue that this is a necessary requirement in order to have free will, in the sense that I am privately selecting this action over that action. And that, I think, relates to a phrase that was exemplified by that first simulation where the little agent was writing stuff. She was creating her own sensorium. Everything that happened came from inside her head. So, in a sense, there is also an inbuilt autonomy, even at the level of this kind of reflexive behavior. But that agent could not choose which letters to write. She could only write J and A. Whereas the second agent, the second simulated agent, would actually choose where to look. And in so choosing, you could argue evinced an elemental kind of free will that only she knew about, because it was based upon her beliefs, that because of the expected information gain. So the expected information gain is a function of what you believe now and how that belief will change if you did that. So it's private to you, and it's also completely context and time sensitive. So you'll never have the same information gained twice. So that's why it's incredibly private to you. So I think that kind of agent, with that kind of generative model, would be a necessary aspect before you could talk about free will and selection. And I would argue also consciousness, but there are all sorts of different levels of consciousness, which you you'd have. Well, I think you better go and read the literature and see what your favourite theory is. But certainly the free will and agency, I think that's very clear. I think there is a bright line between merely reflexive active inference, and you could actually argue state action policies and reinforcement learning, and then Bayesian RL or more planning as inference of the kind that's, if you like, generalized by active inference with this expected free energy. I think you're only going to find free will and agency on things that can plan.
Thank you. Thank you very much. Thank you.
We have a few more questions from the audience that I'm giving them the permission to ask.
Hi, can you hear me?
Yes.
Yeah, thank you for your great presentation. Actually, I want to ask about my state. I want to know your opinion about this statement. This statement is about the relation between reinforcement learning and active inference framework. I think to build a kind of bridge between these two fields, we can say that maybe the notion of task can be deemed somehow as a kind of generative model, and the hierarchical structure over tasks can be seen as a hierarchical structure over generative models. So can we say that the notion of task is somehow the same as the notion of generative model? Because in the field of reinforcement learning, we usually hear the notion of task and rewarding, and the hallmark of a task is the rewarding system and the environment. But in the framework of active inference, I think that the hallmark is generative model and the notion of uncertainty. Can we say these notions are equivalent or not?
Yes, I think you can, because the generative model can always be, just technically, the generative model is just a probabilistic statement of the relationship between cause and consequence, unobservable latent states that you can't see, hidden states or latent states, and observable consequences that could include reward, for example. So you just write down a joint probability distribution over external states, under the Markov blanket partition, the latent or the hidden states hidden behind the Markov blanket, and the observable states that you have access to, that you can actually measure. And once you've written that down, you can always rewrite that as a likelihood, the probability of my sensory states given the latent states times the prior distribution over the latent states. And if you can do that, then you can actually write the reward and implicit the task into the prize. So from the point of view of the generative model, you would install the task in terms of the prior preferences about the end outcomes of a particular set of engagements. So exactly in the same way that you described in terms of reinforcement learning, the task is specified by the outcomes that you expect to happen, that you assign or you reward. In exactly the same way, you can write down the prior preferences over outcomes in the future that you expect to happen, and those become the expected value part of the expected free energy, such that the agent is more likely to choose those policies that will obtain those outcomes that may be quite simply scored on a reward channel, for example. You can also write down rewarded latent states provided you've already learned the generative model. But that takes us outside, I think, reinforcement learning, because the whole point of reinforcement learning is that you can only instruct the task or reward or reinforce the behavior by supplying special or privileged outcomes, observations that are the reward themselves. So in active inference, that would require you to write down prior preferences over the outcomes that underwrite that risk divergence, or specify the expected value. So if we just remember that risk, that divergence, that KL control divergence, you're writing down effectively the rewards in output space, um, as a target, and then you're acting in a way that what would happen if I did this action in terms of my posterior beliefs about the outcomes, trying to bring that as close as possible to the rewarded outcomes. And what you should get out of that is an agent will look as if it's performing that task that you've specified in terms of the constraints on the consequences of action. So, it comes back, I think, to the answer to the first question, where is reward in active inference? Well, it's just basically a statement of the kind of thing this agent is as defined by what it works towards. So you can always define it in terms of a probability distribution over the outcomes this kind of agent that does this kind of task would expect to see. So all you have to do is to write it in terms of a probability distribution. Is that what you implied?
If I understand correctly, you say that task can be encoded in the prior of the generative models at the preferences we have over the states. So somehow the reward system in the task can be represented as a kind of prior over states. And given that, we can say that the hierarchical structure over the task, the way we, for example, decompose a task to several subtasks as a kind of a strategy usually used in reinforcement learning, we can say the equivalent structure should be mm, should be moved to the hierarchical structure over priors or hierarchical generative models. But I think that maybe I want to know that if there is a research about in the field of active inference about this decomposition, because the way we decompose these tasks in the terms of priors or in the terms of hierarchical structure over generative models. Even in the field of reinforcement learning, there is little research about hierarchical reinforcement learning, but I think that maybe it is promising to build this hierarchical structure in the field of active inference or predictive coding.
Yeah.
I want to know that if there is a robust research in this field about this topic.
Yes, no, excellent question. And you're absolutely right. When you have a hierarchical generative model, you would specify your prior preferences at each level of the hierarchy. And as you say, that would afford some kind of chunking or decomposition,
Yeah.
usually because the higher levels you tick over more slowly than the lower levels. So you would specify your prior preferences in the output space of each level, which of course is the input space of the level below. In answer to your question, this is an active area of research. The best work that I'm aware of is in usually neurorobotics, and I would look at the work of the Ghent group, Ghent, and specifically the group led by Tim Verbelen, Vebelen, who's a roboticist. But he's also worked with colleagues in the Netherlands. So, in answer to your question, there is not a large literature in this area, but this is exactly the kind of application of active inference that people are now um, trying to deploy, understand, and engineer specifically the separation of temporal scales and getting a hierarchical decomposition of multiple tasks. And people are working actively on this. So I just look at active inference robotics. There is another small literature comparing and contrasting non-hierarchical active inference with reinforcement learning, but I think you're probably more interested in active inference under these deep generative models, where
Yeah.
the very depth implies that you've now got empirical priors or inductive biases at every level. And those, of course, afford the opportunity to write in preference priors at every level. And that, as you intimate, now affords a kind of decomposition of sequential tasks. It's interesting just to note that in solving the expected free energy problem, you are effectively doing sequential policy optimization. So it's no longer a state action policy, but it's sequential policy optimization, because as you go through your policy, you're changing your beliefs because you're resolving uncertainty. But you, um, um, so the, it's quite a difficult problem in the sense that you have to imagine what I would see and what I would know if I did that in order to choose the best sequence. But the advantage is in solving the sequential policy optimization, sequence of actions that get you to your reward or to your goal. And that goal could be epistemic or information gain, or it could just be securing expected reward or value. Um, in getting from there to there, you have to the order matters. So even within each level, you'll have a sequential policy optimization. And now you've got sequential policy optimizations of sequential policy optimizations that gives you a lot of flexibility, but it's not, I repeat, I can't point you to a journal of this, but I can point you to people who have been writing in that area. And I repeat, that would be the neurorobotics people looking at active inference. Juntani might be another person you might want to look at. Juntani, Juntani, and I think he's now back in Japan at the Riken Institute. He used to be, or possibly Okinawa. He used to be at KAIST in Korea, but he's been writing about this sort of hierarchical approach to optimal behavior in a way that he does describe in terms of active inference, but is also understandable, I think, from a reinforcement learning perspective. And you might find some interesting work. He actually wrote a book published by the Oxford University Press about 2 years ago that might be interesting.
What is the name of the book?
I can't remember. My apologies.
Yeah, okay, okay, no problem,
if you
no problem.
Google his name and his most recent book.
Yeah. Okay, okay. Thank you so much. Thank you so much. Thank you for your great representation. Presentation, sorry. Yeah.
Thank you, Professor. I think our time is up, but we have two more questions from the audience. I wanted to ask if we can go about them or we have to finish on time.
No, I'd be happy to answer two more questions.
Okay, let me give them.
Hello, can you hear me?
Yes, I can.
Thank you for your great presentation. I try to ask my question quickly. As a part of my PhD research, we are going to apply predictive coding approach to emotion and emotional processing and using experimental paradigms. And I just want to know your opinion about this and how do you see this path, and do you have any consideration for us to know, as there's lack of experimental evidence in this field, and also we are aware that this approach has been applied to music perception, but we are going to use visual stimuli in emotional perception.
Right. I see. Are you going to try and induce emotions, or are the stimuli going to be have an emotional valence?
I'm sorry?
Uh, What kind of stimuli will you use? Are they valenced or emotional stimuli
Yes, yes,
themselves?
yes, yes.
I see. I see.
Valence. We are going to control other variables and manipulate emotions using valence, change in valence.
Right. And is your question about how you would use predictive coding to understand real brain responses, or are you trying to build a machine that will recognize emotions?
No, no, we are going to use a neural response using EEG.
Oh, I see. Yeah. Um, right. So emotion. Yeah. Well, I mean, yeah, it's a fascinating area. Then then I think the role of predictive coding would be to really interpret neuronal responses in terms of precision-weighted prediction errors.
Yeah.
And um, the precision weighting, I think, is quite important here. We didn't talk about it very much in the presentation I gave, but most of the um, narrative literature on predictive coding as a metaphor or an explanation or description of neuronal responses um, focuses on precision weighted prediction errors, where the precision can be read as something that is affording confidence or inverse noisiness or variance to certain prediction errors. So from the point of view of the Bayesian mechanics, it's like setting the Kalman gain in a Bayesian filter. From the point of view of neurophysiology, it's often read in terms of the excitability of neurons encoding prediction errors. And the degree to which they activate as reflected in the amplitude, say, of a mismatch negativity or a particular waveform in EEG. From a psychological point of view, it's often read in terms of attentional selection. So if I increase the precision or I estimate or predict the precision of this attribute of the sensory input to be higher, then effectively I am selectively attending to this kind of attribute or this modality. And conversely, if I decrease the precision, then I get into the game of the world of sensory attenuation. So I think in terms of emotional stimuli, usually emotional stimuli are used to induce um, a particular context or affect that you could think of in terms of setting the attentional set. So you'd be looking for differences in the um, amplitude of event-related responses to the same kinds of stimuli, but um, different because people have assigned more precision to them in one emotional context following emotional induction, for example, relative to another context. So I'm not sure that's going to be very useful, but that's usually how people apply predictive coding to interpreting EEG experiments. They think of it in terms of the EEG signals reporting the reporting precision-weighted prediction errors that have been elicited by careful experimental design. So normally people have a sort of oddball paradigm or a mismatch negativity-like paradigm that then they cross with another experimental factor that would, I presume, for you, be emotion. So you produce, for example, if you used an oddball paradigm, you might have a series of happy faces with an occasional um, sad face, and that would be an oddball elicited in the context of emotional processing. And then you'd repeat it with a series of pictures of fruit with occasional change to a vegetable, which might be a non-emotional. And then you'd be looking for differences in the evoked responses, in particular the mismatch negativities, if elicited by the oddball, and then you attribute that to emotional processing. And if you source reconstructed, you'd be trying to work out where this this prediction of precision came from, and how that was associated with emotional inference or affective inference, and usually that entails the interoceptive hierarchy or the emotional hierarchy. Does that help?
Thank you, thank you. Yes, we came across two studies that use attentional paradigms to study this approach, to employ this approach. But I think our perspective is a little different, but I'm not sure. As we are going to, I'm not sure that you think we can see emotion as change in prediction errors, and we don't use attention, precision, prediction error precision. Um, do you think, is it possible to not study emotional in respect of attentional processes?
Well, no, I certainly think it's possible. It's just that if the emotion is an attribute of the stimulus as opposed to the observer, then yes, it would certainly be possible to look at prediction errors in the domain of the effective valence of the stimuli. What I was thinking, though, was that if the emotion is an attribute of the current perceptual and attentional set of the subject, then that's usually better thought of in terms of the context in which you're processing stimuli. And that usually entails, you don't have to work explicitly with precision or attention, but more just the context in which these prediction errors are being generated. And you can either describe it in terms of precision weighting or in terms of attention, or in terms of gain control. It's just that the precision usually is the precision is usually associated with the context. So I don't know your experimental design, but I'm just making a distinction between the emotional state of a subject in terms of subject intention and attention perceptual set, and the emotional attributes of the stimuli. And if you're talking about the perceptual set of the subject and the emotional state of the subject, then you may want to think about precision. But if you're talking about just the stimuli, then you probably don't have to worry about the precision.
Yes. Thank you very much.
We have another question from the audience, but unfortunately he cannot open his mic, so I'm gonna read from the chat. He said, I'm a researcher on the field of social cognition. How could active inference and free energy principle be used for studying our perception about our social status in the social hierarchy of research? Social hierarchy research.
I see. So there is a community of people applying active inference to interpersonal inference and dyadic inference, and indeed right through to the level of social norms and social judgments and attribution. I think the best thing to do, to find that literature and the key authors, a lot of whom come from Toronto in Canada, would be to go to that website I mentioned before, which is the Active Inference Institute, and just see if they have a repository or any working groups looking specifically about social or multi-agent applications of active inference. So there is quite a lot of work ranging from applications to psychotherapy and dyadic interactions, right through to swarming behavior in pure ethology, recently there was a PNAS paper by my colleague Connor Hines, just looking at how collectives swarm together using inference about themselves in the context of other things like themselves. So there is quite a large literature on that, and I think you just have to sort of explore the literature and find out what specifically is going to be useful in terms of hierarchical inference. How do I infer that you are hierarchically higher or lower than me? And how much does that depend upon shared narratives and shared generative models that are scaffolded by cultural niche construction or installing particular kinds of generative models through transcultural or transgenerational um, transmission, very much in the spirit of evolutionary psychology. So there is a literature out there, but I think you're going to have to discover it yourself. Does that help?
Thank you, dear professor. I think the person, I don't see any response from that person. But thank you very much. I just have two very quick closing question. If you have time, I can ask. Okay. My first question is from the way that you understand the intelligence from studying the brain, the neuroscience. How do you see the current wave of AI that we build giant prediction machines from all the human knowledge and do some reinforcement learning on top of it and try to uh, try to come up with new things in this way and make different experts and try to do agent try to cooperate with them and solve bigger problems with a community of these prediction machines that we fine tune them with LLM with reinforcement learning. I just want to ask, how do you see this from the way that you understand the brain? How do you see this current wave of AI? And do you think this trend would plateau in the future? And what do you think are missing from the way that we understand the intelligence from the living intelligence? What do you think is missing from the way that we design the intelligence systems today?
Right. That's not a short question. Take about a day to answer that, possibly.
Okay.
Um, so, what is missing? I think it's the ability to plan in a simple and authentic way. I don't think large language models have the capacity to imagine their own futures. So they're not true agents. They're certainly beautiful and very, very functional and expressive prediction machines. Incredibly powerful prediction machines, but they can't plan because they don't have a generative model of their own future. And furthermore, it's because they're not built explicitly on an explainable generative model. There's no encoding of uncertainty, so they don't know how to resolve their own uncertainty, which is why you have to give them everything, so they don't have to choose. So I imagine that technology will plateau, and it will plateau in a way which I think is distinct from natural intelligence, because natural intelligence does the opposite. It's fast and frugal, it's smart, and just requires sparse data, but crucially, data that are, if you like, chosen very carefully to resolve what this particular large language model doesn't know. So I sometimes joke, when large language models start prompting me, I'll accept that they're becoming more biomimetic and more. But I think it's going in a different direction, and it will saturate. But it's already attained incredible performance. I wouldn't worry about it saturating. It's already probably one of the most beautiful inventions or engineering inventions of this century. But I don't think that's biomimetic. What you'll see is smarter, smaller, and interestingly, as you intimated, interactions being lots of smart small things. So you've got distributed a little ecosystem of agents all doing their thing. And we will be part of that ecosystem. But that will be a different kind of intelligence, I think.
Okay, okay. Thank you so much. And My final question is, if you want to start, imagine yourself that starting from 2025, and you have all these curiosities, and you want to go about your research career. How would you choose your path? What do you go on and major on? What courses do you take? What books do you read? What do you plan if you want to start today and have these curiosities and want to be a researcher that have something to say, for example, in 20, 30 years into the future?
That's again an excellent question. Uh,
But not short.
well, no, I know, no, there is a short answer to this
Uh,
one. It's keep your options open. So your foundational training is crucial, but it should be as broad as possible because you've then got the opportunity to explore and narrow down as you get older and older. So if you don't have that broad foundational training, you can't pick what is going to be useful and you can't see the connections between things. So you don't have to do this and this and this and this, but just do a lot of things that are very far apart. So do a course in philosophy, do a course in maths, do a course in quantum physics, do a course in dynamical systems. Just make sure you've covered all the bases. It doesn't have to be very deep. So I spend most of my life now talking and lecturing and writing about um, physics. And all that I write about, I have got from Wikipedia because I have completely forgotten the quantum physics I did when I was 20. You don't have to remember, but I know I can do it. And of course, it's easy to relearn. So you don't have to do all these things very deeply, but just expose yourself to them so you know they're there in a way that you can come back to when you realize that's what I need in order to sort of join that dot or to make this conceptual link or to find the right methodology for progressing to the next level. I'll just close by reinforcing that notion in reference to what was on Richard Feynman's blackboard at the point of his death. So the famous quote is, "That which I cannot create, I do not understand," which is usually read in terms of the importance of having a generative model. You have to be able to generate something before you can understand it. The thing underneath it, I think, was probably even more important. Know how to solve every problem that has been solved. So that means you've got to read everything. Again, I repeat, not deeply, but just know it's out there, know it's been solved, and then when you need to in later life, you can come back to it.
Thank you, Professor. I think it was a great answer to my question. So I'm very much thank you for your time and accepting our invitation and spending time with us. I think we are 20 minutes far from that time, and I'm very much thankful for that.
My pleasure. Thank you very much for hosting me.
Thank you. Thank you. Have a good rest of the day.
Thank you
Bye.
very much.
Bye.
I'll go and do that. Bye bye.
Thanks. Bye.